Electric Discharges, Waves and Impulses. Preface. In the following I am trying to give a short outline of those phenomena which have become the most important to the electrical engineer, as on their understanding and control depends the further successful advance of electrical engineering. The art has now so far advanced that the phenomena of the steady flow of power are well understood. Generators, motors, transforming devices, transmission and distribution conductors can, with relatively little difficulty, be calculated, and the phenomena occurring in them under normal conditions of operation predetermined and controlled. Usually, however, the limitations of apparatus and lines are found not in the normal condition of operation, the steady flow of power, but in the phenomena occurring under abnormal though by no means unfrequent conditions, in the more or less transient abnormal voltages, currents, frequencies, etc., and the study of the laws of these transient phenomena, the electric discharges, waves, and impulses, thus becomes of paramount importance. In a former work, Theory and Calculation of Transient Electric Phenomena and Oscillations, I have given a systematic study of these phenomena, as far as our present knowledge permits, which by necessity involves to a considerable extent the use of mathematics. As many engineers may not have the time or inclination to a mathematical study, I have endeavored to give in the following a descriptive exposition of the physical nature and meaning, the origin and effects, of these phenomena, with the use of very little and only the simplest form of mathematics, so as to afford a general knowledge of these phenomena to those engineers who have not the time to devote to a more extensive study, and also to serve as an introduction to the study of transient phenomena. I have, therefore, in the following developed these phenomena from the physical conception of energy, its storage and readjustment, and extensively used as illustrations oscillograms of such electric discharges, waves, and impulses, taken on industrial electric circuits of all kinds, as to give the reader a familiarity with transient phenomena by the inspection of their record on the photographic film of the oscillograph. I would therefore recommend the reading of the following pages as an introduction to the study of transient phenomena, as the knowledge gained thereby of the physical nature materially assists in the understanding of their mathematical representation, which latter obviously is necessary for their numerical calculation and predetermination. 66. The book contains a series of lectures on electric discharges, waves, and impulses, which was given during the last winter to the graduate classes of Union University as an elementary introduction to and translation from mathematics into English of the theory and calculation of transient electric phenomena and oscillations. Here too has been added a chapter on the calculation of capacities and inductances of conductors, since capacity and inductance are the fundamental quantities on which the transients depend. In the preparation of the work, I have been materially assisted by Mr. C. M. Davis, M.E.E., who kindly corrected and edited the manuscript and illustrations, and to whom I wish to express my thanks. Lecture 1. Nature and Origin of Transients. Electrical engineering deals with electric energy and its flow, that is, electric power. Two classes of phenomena are met, permanent and transient phenomena. To illustrate, let G in Figure 1 be a direct current generator, which over a circuit A connects to a load L, as a number of lamps, etc. In the generator G, the line A, and the load L, a current I, flows, and voltages E, exist, which are constant, or permanent, as long as the conditions of the circuit remain the same. If we connect in some more lights, or disconnect some of the load, we get a different current I, and possibly different voltages E, but again I and E are permanent, that is, remain the same as long as the circuit remains unchanged. Let, however, in Figure 2, a direct current generator G be connected to an electrostatic condenser C. Before the switch S is closed, and therefore also in the moment of closing the switch, no current flows in the line A. Immediately after the switch S is closed, current begins to flow over line A into the condenser C, charging this condenser up to the voltage given by the generator. When the condenser C is charged, the current in the line A and the condenser C is zero again. That is, the permanent condition before closing the switch S, and also some time after the closing of the switch, is zero current in the line. Immediately after the closing of the switch, however, current flows for a more or less short time. With the condition of the circuit unchanged, the same generator voltage, the switch S closed on the same circuit, the current nevertheless changes, increasing from zero, at the moment of closing the switch S, to a maximum, and then decreasing again to zero, while the condenser charges from zero voltage to the generator voltage. We then here meet a transient phenomenon, in the charge of the condenser from a source of continuous voltage. Commonly, transient and permanent phenomena are superimposed upon each other. For instance, if in the circuit figure 1, we close the switch S connecting a fan motor F, at the moment of closing the switch S the current in the fan motor circuit is zero. It rapidly rises to a maximum, the motor starts, its speed increases while the current decreases, until finally speed and current become constant, that is, the permanent condition is reached. The transient, therefore, appears as intermediate between two permanent conditions, in the above instance, the fan motor disconnected, and the fan motor running at full speed. The question then arises, why the effect of a change in the conditions of an electric circuit does not appear instantaneously, but only after a transition period, requiring a finite, though frequently very short, time. 2. Consider the simplest case, an electric power transmission. Figure 3. In the generator G, electric power is produced from mechanical power, and supplied to the line A. In the line A some of this power is dissipated, the rest transmitted into the load L, where the power is used. The consideration of the electric power in generator, line, and load does not represent the entire phenomenon. While electric power flows over the line A, there is a magnetic field surrounding the line conductors, and an electrostatic field issuing from the line conductors. The magnetic field and the electrostatic or dielectric field represent stored energy. Thus, during the permanent conditions of the flow of power through the circuit figure 3, there is electric energy stored in the space surrounding the line conductors. There is energy stored also in the generator and in the load, for instance, the mechanical momentum of the revolving fan in figure 1, and the heat energy of the incandescent lamp filaments. The permanent condition of the circuit, figure 3, thus represents not only flow of power, but also storage of energy. When the switch S is open, and no power flows, no energy is stored in the system. If we now close the switch, before the permanent condition corresponding to the closed switch can occur, the stored energy has to be supplied from the source of power, that is, for a short time power, in supplying the stored energy, flows not only through the circuit, but also from the circuit into the space surrounding the conductors, etc. This flow of power, which supplies the energy stored in the permanent condition of the circuit, must cease as soon as the stored energy has been supplied, and thus is a transient. Inversely, if we disconnect some of the load L in figure 3, and thereby reduce the flow of power, a smaller amount of stored energy would correspond to that lesser flow, and before the conditions of the circuit can become stationary or permanent, corresponding to the lessened flow of power, some of the stored energy has to be returned to the circuit, or dissipated, by a transient. Thus the transient is the result of the change of the amount of stored energy, required by the change of circuit conditions, and is the phenomenon by which the circuit readjusts itself to the change of stored energy. It may thus be said that the permanent phenomena are the phenomena of electric power, the transients the phenomena of electric energy. 3. It is obvious, then, that transients are not specifically electrical phenomena, but occur with all forms of energy, under all conditions where energy storage takes place. Thus, when we start the motors propelling an electric car, a transient period of acceleration appears between the previous permanent condition of standstill and the final permanent condition of constant speed running. When we shut off the motors, the permanent condition of standstill is not reached instantly, but a transient condition of deceleration intervenes. When we open the water gates leading to an empty canal, a transient condition of flow and water level intervenes while the canal is filling, until the permanent condition is reached. Thus in the case of the fan motor in instance figure 1, a transient period of speed and mechanical energy appeared while the motor was speeding up and gathering the mechanical energy of its momentum. When turning on an incandescent lamp, the filament passes a transient of gradually rising temperature. Just as electrical transients may, under certain conditions, rise to destructive values, so transients of other forms of energy may become destructive, or may require serious consideration, as, for instance, is the case in governing high-head water powers. The column of water in the supply pipe represents a considerable amount of stored mechanical energy, when flowing at velocity, under load. If, then, full load is suddenly thrown off, it is not possible to suddenly stop the flow of water, since a rapid stopping would lead to a pressure transient of destructive value, that is, burst the pipe. Hence the use of surge tanks, relief valves, or deflecting nozzle governors. Inversely, if a heavy load comes on suddenly, opening the nozzle wide does not immediately take care of the load, but momentarily drops the water pressure at the nozzle, while gradually the water column acquires velocity, that is, stores energy. The fundamental condition of the appearance of a transient thus is such a disposition of the stored energy in the system as differs from that required by the existing conditions of the system, and any change of the condition of a system, which requires a change of the stored energy, of whatever form this energy may be, leads to a transient. Electrical transients have been studied more than transients of other forms of energy because, a. Electrical transients generally are simpler in nature, and therefore yield more easily to a theoretical and experimental investigation. b. The theoretical side of electrical engineering is further advanced than the theoretical side of most other sciences, and especially, c. The destructive or harmful effects of transients in electrical systems are far more common and more serious than with other forms of energy, and the engineers have therefore been driven by necessity to their careful and extensive study. 4. The simplest form of transient occurs where the effect is directly proportional to the cause. This is generally the case in electric circuits, since voltage, current, magnetic flux, etc. are proportional to each other, and the electrical transients therefore are usually of the simplest nature. In those cases, however, where this direct proportionality does not exist, as for instance in inductive circuits containing iron, or in electrostatic fields exceeding the corona voltage, the transients also are far more complex, and very little work has been done, and very little is known, on these more complex electrical transients. Assume that in an electric circuit we have a transient current, as represented by curve I1 in figure 4, that is, some change of circuit condition requires a readjustment of the stored energy, which occurs by the flow of transient current I. This current starts at the value I1, and gradually dies down to 0. Assume now that the law of proportionality between cause and effect applies, that is, if the transient current started with a different value, I2, it would traverse a curve I1, which is the same as curve I1 except that all values are changed proportionally, by the ratio I2 over I1, that is I equals I times I2 over I1. Starting with current I, the transient follows the curve I. Starting with I2, the transient follows the proportional curve I. At some time, t, however, the current I has dropped to the value I2, with which the curve I started. At this moment t, the conditions in the first case, of current I, are the same as the conditions in the second case, of current I, at the moment t, that is, from t, onward, curve I is the same as curve I from time t onward. Since I is proportional to I from any point t onward, curve I is proportional the same curve I from t onward. The exponential curve thus is the expression of the simplest form of transient. This explains its common occurrence in electrical and other transients. Consider, for instance, the decay of radioactive substances. The radiation, which represents the decay, is proportional to the amount of radiating material. It is dm over dt equals cm, which leads to the same exponential function. Not all transients, however, are of this simplest form. For instance, the deceleration of a ship does not follow the exponential, but at high velocities the decrease of speed is a greater fraction of the speed than during the same time interval at lower velocities, and the speed-time curves for different initial speeds are not proportional to each other, but are as shown in Figure 5. The reason is that the frictional resistance is not proportional to the speed, but to the square of the speed. 5. Two classes of transients may occur. 1. Energy may be stored in one form only, and the only energy change which can occur thus is an increase or a decrease of the stored energy. 2. Energy may be stored in two or more different forms, and the possible energy changes thus are an increase or decrease of the total stored energy, or a change of the stored energy from one form to another. Usually both occur simultaneously. An instance of the first case is the acceleration or deceleration of a train, or a ship, etc. Here energy can be stored only as mechanical momentum, and the transient thus consists of an increase of the stored energy, during acceleration, or of a decrease, during deceleration. Thus also in a low-voltage electric circuit of negligible capacity, energy can be stored only in the magnetic field, and the transient represents an increase of the stored magnetic energy, during increase of current, or a decrease of the magnetic energy, during a decrease of current. An instance of the second case is the pendulum, Figure 6, with the weight at rest in maximum elevation. All the stored energy is potential energy of gravitation. This energy changes to kinetic mechanical energy until in the lowest position, A, when all the potential gravitational energy has been either converted to kinetic mechanical energy or dissipated. Then, during the rise of the weight, that part of the energy which is not dissipated again changes to potential gravitational energy, at C, then back again to kinetic energy, at A, and in this manner the total stored energy is gradually dissipated, by a series of successive oscillations or changes between potential, gravitational and kinetic mechanical energy. Thus in electric circuits containing energy stored in the magnetic and in the dielectric field, the change of the amount of stored energy, decrease or increase, frequently occurs by a series of successive changes from magnetic to dielectric and back again from dielectric to magnetic stored energy. This for instance is the case in the charge or discharge of a condenser through an inductive circuit. If energy can be stored in more than two different forms, still more complex phenomena may occur, as for instance in the hunting of synchronous machines at the end of long transmission lines, where energy can be stored as magnetic energy in the line and apparatus, as dielectric energy in the line, and as mechanical energy in the momentum of the motor. 6. The study and calculation of the permanent phenomena in electric circuits are usually far simpler than are the study and calculation of transient phenomena. However, only the phenomena of a continuous current circuit are really permanent. The alternating current phenomena are transient, as the EMF continuously and periodically changes, and with it the current, the stored energy, etc. The theory of alternating current phenomena, as periodic transients, thus has been more difficult than that of continuous current phenomena, until methods were devised to treat the periodic transients of the alternating current circuit as permanent phenomena, by the conception of the effective values, and more completely by the introduction of the general number or complex quantity, which represents the periodic function of time by a constant numerical value. In this feature lies the advantage and the power of the symbolic method of dealing with alternating current phenomena, the reduction of a periodic transient to a permanent or constant quantity. For this reason, wherever periodic transients occur, as in rectification, commutation, etc., a considerable advantage is frequently gained by their reduction to permanent phenomena, by the introduction of the symbolic expression of the equivalent sine wave. Hereby most of the periodic transients have been eliminated from consideration, and there remain mainly the non-periodic transients, as occur at any change of circuit conditions. Since they are the phenomena of the readjustment of stored energy, study of the energy storage of the electric circuit, that is, of its magnetic and dielectric field, is of first importance. Lecture 2. The electric field. 7. Let, in Figure 7, a generator G transmit electric power over line A into a receiving circuit L. While power flows through the conductors A, power is consumed in these conductors by conversion into heat, represented by I2R. This, however, is not all, but in the space surrounding the conductor certain phenomena occur, magnetic and electrostatic forces appear. The conductor is surrounded by a magnetic field, or a magnetic flux, which is measured by the number of lines of magnetic force. With a single conductor, the lines of magnetic force are concentric circles, as shown in Figure 8. By the return conductor, the circles are crowded together between the conductors, and the magnetic field consists of eccentric circles surrounding the conductors, as shown by the drawn lines in Figure 9. An electrostatic, or, as more properly called, dielectric field, issues from the conductors, that is, a dielectric flux passes between the conductors, which is measured by the number of lines of dielectric force. With a single conductor, the lines of dielectric force are radial straight lines, as shown dotted in Figure 8. By the return conductor, they are crowded together between the conductors, and form arcs of circles, passing from conductor to return conductor, as shown dotted in Figure 9. The magnetic and the dielectric field of the conductors both are included in the term electric field, and are the two components of the electric field of the conductor. 8. The magnetic field or magnetic flux of the circuit, P, is proportional to the current, with a proportionality factor, L, which is called the inductance of the circuit. Phi equals Li. The magnetic field represents stored energy W. To produce it, power, P, must therefore be supplied by the circuit. Since power is current times voltage, P equals EI. To produce the magnetic field of the current I, a voltage E must be consumed in the circuit, which with the current I gives the power P, which supplies the stored energy W of the magnetic field Phi. This voltage E is called the inductance voltage or voltage consumed by self-induction. Since no power is required to maintain the field, but power is required to produce it, the inductance voltage must be proportional to the increase of the magnetic field. 9. Exactly analogous relations exist in the dielectric field. The dielectric field, or dielectric flux, Y, is proportional to the voltage E, with a proportionality factor, C, which is called the capacity of the circuit. The dielectric field represents stored energy, W. To produce it, power, P, must, therefore, be supplied by the circuit. Since power is current times voltage. To produce the dielectric field of the voltage E, a current I must be consumed in the circuit, which with the voltage E gives the power P, which supplies the stored energy W of the dielectric field. This current I is called the capacity current, or, wrongly, charging current or condenser current. Since no power is required to maintain the field, but power is required to produce it, the capacity current must be proportional to the increase of the dielectric field. As seen, the capacity current is the exact analogy, with regard to the dielectric field, of the inductance voltage with regard to the magnetic field, the representations in the electric circuit, of the energy storage in the field. The dielectric field of the circuit thus is treated and represented in the same manner, and with the same simplicity and perspicuity, as the magnetic field, by using the same conception of lines of force. Unfortunately, to a large extent in dealing with the dielectric fields the prehistoric conception of the electrostatic charge on the conductor still exists, and by its use destroys the analogy between the two components of the electric field, the magnetic and the dielectric, and makes the consideration of dielectric fields unnecessarily complicated. There obviously is no more sense in thinking of the capacity current as current which charges the conductor with a quantity of electricity, than there is of speaking of the inductance voltage as charging the conductor with a quantity of magnetism. But while the latter conception, together with the notion of a quantity of magnetism, etc. has vanished since Faraday's representation of the magnetic field by the lines of magnetic force, the terminology of electrostatics of many textbooks still speaks of electric charges on the conductor, and the energy stored by them, without considering that the dielectric energy is not on the surface of the conductor, but in the space outside of the conductor, just as the magnetic energy. 10. All the lines of magnetic force are closed upon themselves, all the lines of dielectric force terminate at conductors, as seen in Figure 8, and the magnetic field and the dielectric field thus can be considered as a magnetic circuit and a dielectric circuit. To produce a magnetic flux, a magnetomotive force F is required. Since the magnetic field is due to the current, and is proportional to the current, or, in a coiled circuit, to the current times the number of turns, magnetomotive force is expressed in current turns or ampere turns. If F is the mmfL, the length of the magnetic circuit, energized by F, is called the magnetizing force, and is expressed in ampere turns per cm, or industrially sometimes in ampere turns per inch. In empty space, and therefore also, with very close approximation, in all non-magnetic material, F, ampere turns per centimeter. Length of magnetic circuit produced 3 equals 4 pi F10 superscript 1 lines of magnetic force per square centimeter section of the magnetic circuit. Here the factor 10 to the power minus 1 results from the ampere being 10 to the power minus 1 of the absolute or CGS. Unit of current is called the magnetic field intensity. It is the magnetic density, that is, the number of lines of magnetic force per cm superscript 2, produced by the magnetizing force of F ampere turns per centimeter, in empty space. The magnetic density, in lines of magnetic force per cm superscript 2, produced by the field intensity in any material is where mu is a constant of the material, magnetic conductivity, and is called permeability. Mu1 or very nearly so for most materials, with the exception of very few, the so-called magnetic materials, iron, cobalt, nickel, oxygen, and some alloys and oxides of iron, manganese, and chromium. If then A is the section of the magnetic circuit, the total magnetic flux is phi equals AB. Obviously, if the magnetic field is not uniform, equations 13 and 16 would be correspondingly modified. F in 13 would be the average magnetizing force, while the actual magnetizing force would vary, being higher at the denser, and lower at the less dense, parts of the magnetic circuit, F equals dF over dL in 16. The magnetic flux and would be derived by integrating the densities over the total section of the magnetic circuit. Point 2. Entirely analogous relations exist in the dielectric circuit. To produce a dielectric flux, an electromotive force E is required, which is measured in volts. The EMF per unit length of the dielectric circuit then is called the electrifying force or the voltage gradient, and is G equals E over L, unit distance with unit force. The unit field intensity, then, was defined as the field intensity at unit distance from unit magnetic mass, and represented by one line, or rather, tube, of magnetic force. The magnetic flux of unit magnetic mass, or unit magnet pole, hereby became 4 pi lines of force, and this introduced the factor 4 pi into many magnetic quantities. An attempt to drop this factor 4 pi has failed, as the magnetic units were already too well established. The factor 10 to 1 also appears undesirable, but when the electrical units were introduced the absolute unit appeared as too large a value of current as practical unit, and 1/10 of it was chosen as unit, and called ampere. This gives the average voltage gradient, while the actual gradient in a non-uniform field, as that between two conductors, varies, being higher at the denser, and lower at the less dense, portion of the field, and is G equals D over dL, K equals G over alpha pi, then is the dielectric field intensity, and D equals Kk would be the dielectric density, where K is a constant of the material, the electrostatic or dielectric conductivity, and is called the specific capacity or permittivity. For empty space, and thus with close approximation for air and other gases, K equals 1 over v squared, where is the velocity of light. V is equal to 3 times 10 to the power 10. It is customary, however, and convenient, to use the permittivity of empty space as unity, K equals 1. This changes the unit of dielectric field intensity by the factor, and gives, dielectric field intensity, dielectric density, K equals G over 4 pi v squared. Where K equals 1 for empty space, and between 2 and 6 for most solids and liquids, rarely increasing beyond 6. The dielectric flux then is to AD. The simplest electrical transients are those in circuits in which energy can be stored in one form only, as in this case the change of stored energy can consist only of an increase or decrease, but no surge or oscillation between several forms of energy can exist. Such circuits are most of the low and medium voltage circuits, minus 220 volts, 600 volts, and 2200 volts. In them the capacity is small, due to the limited extent of the circuit, resulting from the low voltage, and at the low voltage the dielectric energy thus is negligible, that is, the circuit stores appreciable energy only by the magnetic field. A circuit of considerable capacity, but negligible inductance, if of high resistance, would also give one form of energy storage only, in the dielectric field. The usual high-voltage capacity circuit, as that of an electrostatic machine, while of very small inductance, also is of very small resistance, and the momentary discharge currents may be very considerable, so that in spite of the very small inductance, considerable magnetic energy storage may occur, that is, the system is one storing energy in two forms, and oscillations appear, as in the discharge of the Leyden jar. As represented in Figure 10, a continuous voltage E0 be impressed upon a wire coil of resistance R and inductance L, but negligible capacity. A current I0 equals EO over R flows through the coil and the magnet field Phi0 10 to the power minus 8 equals Li0 over N interlinks with the coil, assuming now that the voltage E0 is suddenly withdrawn, without changing the constants of the coil circuit, as for instance by short-circuiting the terminals of the coil, as indicated at A, with no voltage impressed upon the coil, and thus no power supplied to it, current I and magnetic flux of the coil must finally be zero. However, since the magnetic flux represents stored energy, it cannot instantly vanish, but the magnetic flux must gradually decrease from its initial value P, by the dissipation of its stored energy in the resistance of the coil circuit as I superscript 2R. Plotting, therefore, the magnetic flux of the coil as a function of the time, in Figure 11a, the flux is constant and denoted by Phi0 up to the moment of time where the short circuit is applied, as indicated by the dotted line 2. From then on the magnetic flux decreases, as shown by the curve Phi. Since the magnetic flux is proportional to the current, the latter must follow a curve proportional to P, as shown in Figure 11b. The impressed voltage is shown in Figure 11c as a dotted line, it is EO up to 2, and drops to 0 at 2. However, after a current I flows, an EMF must exist in the circuit, proportional to the current. E equals Re. This is the EMF induced by the decrease of magnetic flux, and is therefore proportional to the rate of decrease of P, that is, to do in the first moment of short circuit, the magnetic flux still dt has full value 0, and the current I thus also full value IO. Hence, at the first moment of short circuit, the induced EMF E must be equal to EO, that is, the magnetic flux, and must begin to decrease at such rate as to induce full voltage EO, as shown in Figure 11c. The three curves, I and E, are proportional to each other, and as E is proportional to the rate of change of 4, must be proportional to its own rate of change, and thus also I and E. That is, the transients of magnetic flux, current, and voltage follow the law of proportionality, hence are simple exponential functions, as seen in Lecture 1. Phi, I, and E decrease most rapidly at first, and then slower and slower, but can theoretically never become zero, though practically they become negligible in a finite time. The voltage E is induced by the rate of change of the magnetism, and equals the decrease of the number of lines of magnetic force, divided by the time during which this decrease occurs, multiplied by the number of turns N of the coil. The induced voltage E times the time during which it is induced thus equals N times the decrease of the magnetic flux, and the total induced voltage, that is, the area of the induced voltage curve, Figure 11c, thus equals N times the total decrease of magnetic flux, that is, equals the initial current IO times the inductance L, et equals eta phi omicron 108 equals LIO whatever, therefore, may be the rate of decrease, or the shape of the curves of Phi, I, and E. The total area of the voltage curve must be the same, and equal to eta phi omicron equals Leo. If then the current I would continue to decrease at its initial rate, as shown dotted in figure 11b, as could be caused, for instance, by a gradual increase of the resistance of the coil circuit, the induced voltage would retain its initial value EO up to the moment of time t equals to t, where the current has fallen to zero, as shown dotted in figure 11c. The area of this new voltage curve would be EOT, and since it is the same as that of the curve E, as seen above, it follows that the area of the voltage curve E is at equals EOT, R minus I minus 0 t, and, combining, 2, and, 3, IO cancels, and we get the value of t equals L over R. That is, the initial decrease of current, and therefore of magnetic flux and of induced voltage, is such that if the decrease continued at the same rate, the current, flux, and voltage would become zero after the time t equals L over R. The total induced voltage, that is, voltage times time, and therefore also the total current and magnetic flux during the transient, are such that, when maintained at their initial value, they would last for the time t equals L over R. Since the curves of current and voltage theoretically never become zero, to get an estimate of the duration of the transient we may determine the time in which the transient decreases to half, or to 1/10, etc. of its initial value. It is preferable, however, to estimate the duration of the transient by the time t, which it would last if maintained at its initial value. That is, the duration of a transient is considered as the time t equals L over R. This time t has frequently been called the time constant of the circuit. The higher the inductance L, the longer the transient lasts, obviously, since the stored energy which the transient dissipates is proportional to L. The higher the resistance R, the shorter is the duration of the transient, since in the higher resistance the stored energy is more rapidly dissipated. Using the time constant t equals L over R, as unit of length for the abscissa, and the initial value as unit of the ordinates, all exponential transients have the same shape, and can thereby be constructed. 4. Usually single-energy transients last an appreciable time, and thereby become of engineering importance only in highly inductive circuits, such as motor fields, magnets, etc. To get an idea on the duration of such magnetic transients, consider a motor field. A 4-polar motor has 8 milliliters, mega lines, of magnetic flux per pole, produced by 6000 ampere turns mmf per pole, and dissipates normally 500 watts in the field excitation. That is, if I0 equals field exciting current, N equals number of field turns per pole, R equals resistance, and L equals inductance of the field exciting circuit, it is hence I0 superscript 2 R equals 500, R equals 500 over I0 superscript 2. That is, the stored magnetic energy could maintain full field excitation for nearly 4 seconds. It is interesting to note that the duration of the field discharge does not depend on the voltage, current, or size of the machine, but merely on, first, the magnetic flux and mmf which determines the stored magnetic energy, and, second, on the excitation power, which determines the rate of energy dissipation. 15. Assume now that in the moment where the transient begins the resistance of the coil in figure 10 is increased, that is, the coil is not short-circuited upon itself, but its circuit closed by a resistance R. Such would, for instance, be the case when opening the switch S. The transients of magnetic flux, current, and voltage are shown as A, B, and C in figure 13. The magnetic flux and therewith the current decrease from the initial values phi and I at the moment t of opening the switch S, on curves which must be steeper than those in figure 11, since the current passes through a greater resistance, R plus R, and thereby dissipates the stored magnetic energy at a greater rate. The impressed voltage EO is withdrawn at the moment 2, and a voltage thus induced from this moment onward, of such value as to produce the current I through the resistance R plus R. In the first moment, the current is still IO, and the induced voltage thus must be E equals I R plus R, while the impressed voltage, before 2, was E equals I R, Hence the induced voltage EO is greater than the impressed voltage EO, in the same ratio as the resistance of the discharge circuit R plus R is greater than the resistance of the coil R through which the impressed voltage sends the current E over E equals R plus R over R. The duration of the transient now is tau equals L over R plus R, that is, shorter in the same proportion as the resistance, and thereby the induced voltage is higher. If R equals infinity, that is, no resistance is in shunt to the coil, but the circuit is simply opened, if the opening were instantaneous, it would be EO, that is, an infinite voltage would be induced. That is, the insulation of the coil would be punctured and the circuit closed in this manner. The more rapid, thus, the opening of an inductive circuit, the higher is the induced voltage, and the greater the danger of break-down. Hence it is not safe to have two rapid circuit opening devices on inductive circuits. To some extent the circuit protects itself by an arc following the blades of the circuit opening switch, and thereby retarding the circuit opening. The more rapid the mechanical opening of the switch, the higher the induced voltage, and further, therefore, the arc follows the switch blades and maintains the circuit. 16. Similar transients as discussed above occur when closing a circuit upon an impressed voltage, or changing the voltage, or the current, or the resistance or inductance of the circuit. A discussion of the infinite variety of possible combinations obviously would be impossible. However, they can all be reduced to the same simple case discussed above, by considering that several currents, voltages, magnetic fluxes, etc., in the same circuit add algebraically, without interfering with each other, assuming, as done here, that magnetic saturation is not approached. If an EMF E produces a current I in a circuit, and an EMF E produces in the same circuit a current I, then the EMF E plus E2 produces the current I plus I2, as is obvious. If now the voltage E plus E2, and thus also the current I plus I2, consists of a permanent term, E and I, and a transient term, E2 and I2, the transient terms E2, I2 follow the same curves, when combined with the permanent terms E1, 1, as they would when alone in the circuit, the case above discussed. Thus, the preceding discussion applies to all magnetic transients. By separating the transient from the permanent term, investigating it separately, and then adding it to the permanent term, the same reasoning also applies to the transient resulting from several forms of energy storage, provided that the law of proportionality of I, E, phi, etc., applies, and makes it possible, in investigating the phenomena during the transition period of energy readjustment, to separate the permanent and the transient term, and discuss them separately. For instance, in the coil shown in Figure 10, let the short circuit A be opened, that is, the voltage E be impressed upon the coil at the moment of time, t. When this is done, current I, magnetic flux phi, and voltage E on the coil are zero. In the final condition, after the transient has passed, the values I, phi, E are reached. We may then, as discussed above, separate the transient from the permanent term, and consider that at the time t, the coil has a permanent current I, permanent flux phi, permanent voltage E, and in addition thereto a transient current, I, a transient flux phi, and a transient voltage, E. These transients are the same as in Fig. 11, only with reverse direction. Thus the same curves result, and to them are added the permanent values I, phi, E. This is shown in Figure 14. A shows the permanent flux phi, and the transient flux phi, which are assumed, up to the time to give the resultant zero flux. The transient flux dies out by the curve phi, in accordance with Figure 11. Phi added to phi gives the curve phi, which is the transient from zero flux to the permanent flux phi. In the same manner B shows the construction of the actual current change I, by the addition of the permanent current IO and the transient current I, which starts from I at t. C then shows the voltage relation, E. The permanent voltage, E, the transient voltage which starts from, E. At T. And E the resultant or effective voltage in the coil, derived by adding E. And E. Lecture 4. Single energy transients in alternating current circuits. Whenever the conditions of an electric circuit are changed in such a manner as to require a change of stored energy, a transition period appears, during which the stored energy adjusts itself from the condition existing before the change to the condition after the change. The currents in the circuit during the transition period can be considered as consisting of the superposition of the permanent current, corresponding to the conditions after the change, and a transient current, which connects the current value before the change with that brought about by the change. That is, if I equals current existing in the circuit immediately before, and E thus at the moment of the change of circuit condition, and I2 equals current which should exist at the moment of change in accordance with the circuit condition after the change, then the actual current I can be considered as consisting of a part or component I2, and a component I2 equals I. The former, I2, is permanent, as resulting from the established circuit condition. The current component IO, however, is not produced by any power supply, but is a remnant of the previous circuit condition, that is, a transient, and therefore gradually decreases in the manner as discussed in paragraph 13, that is, with a duration T equals L over R. The permanent current I2 may be continuous, or alternating, or may be a changing current, as a transient of long duration, etc. The same reasoning applies to the voltage, magnetic flux, etc. Thus, let, in an alternating current circuit traversed by current, I, in figure 15a, the conditions be changed, at the moment t equals 0, so as to produce the current I2. The instantaneous value of the current I at the moment t equals 0 can be considered as consisting of the instantaneous value of the permanent current I2, shown dotted, and the transient I equals I2. The latter gradually dies down, with duration t equals L over R on the usual exponential transient, shown dotted in figure 15. Adding the transient current I to the permanent current 2 gives the total current during the transition period, which is shown in the drawn line in figure 15. As seen, the transient is due to the difference between the instantaneous value of the current in which exists, and that of the current 2 which should exist at the moment of change, and thus is the larger, the greater the difference between the two currents, the previous and the after current. It thus disappears if the change occurs at the moment when the two currents I and 2 are equal, as shown in figure 15b, and is a maximum, if the change occurs at the moment when the two currents in and I have the greatest difference, that is, at a point 1/4 period or 90 degrees distant from the intersection of in and I2, as shown in figure 15c. If the current I is 0, we get the starting of the alternating current in an inductive circuit, as shown in figure 16a, b, c. The starting transient is 0. If the circuit is closed at the moment when the permanent current would be 0, figure 16b, and is a maximum when closing the circuit at the maximum point of the permanent current wave, fig. 16c. The permanent current and the transient components are shown dotted in figure 16, and the resultant or actual current in drawn lines. Applying the preceding to the starting of a balanced three-phase system, we see, in figure 17a, that in general the three transients I degree, I2, and I3 degree of the three-phase currents I2, I3 are different, and thus also the shape of the three resultant currents during the transition period. Starting at the moment of zero current of one phase, I, fig. 17b, there is no transient for this current, while the transients of the other two currents, I2 and I3, are equal and opposite, and near their maximum value. Starting, in figure 17c, at the maximum value of one current I3, we have the maximum value of transient for this current I3 degree, while the transients of the two other currents, I and I2, are equal, have half the value of I3 degree, and are opposite in direction thereto. In any case, the three transients must be distributed on both sides of the zero line. This is obvious, if I, I2, and I3 are the instantaneous values of the permanent three-phase currents. In Figure 17, the initial values of their transients are I, I2, and I3. Since the sum of the three-phase currents at every moment is 0, the sum of the initial values of the three transient currents also is 0. Since the three transient curves I degree, I2, I3 degree are proportional to each other, as exponential curves of the same duration t equals L over R, and the sum of their initial values is 0, it follows that the sum of their instantaneous values must be 0 at any moment, and therefore the sum of the instantaneous values of the resultant currents, shown in drawn line, must be 0 at any moment, not only during the permanent condition, but also during the transition period existing before the permanent condition is reached. It is interesting to apply this to the resultant magnetic field produced by three equal three-phase magnetizing coils placed under equal angles, that is, to the starting of the three-phase rotating magnetic field, or in general any polyphase rotating magnetic field. As is well known, three equal magnetizing coils, placed under equal angles and excited by three-phase currents, produce a resultant magnetic field which is constant in intensity, but revolves synchronously in space, and thus can be represented by a concentric circle A, Figure 18. This, however, applies only to the permanent condition. In the moment of start, all the three currents are 0, and their resultant magnetic field thus also 0, as shown above. Since the magnetic field represents stored energy and thus cannot be produced instantly, a transient must appear in the building up of the rotating field. This can be studied by considering separately the permanent and the transient components of the three currents, as is done in the preceding. Let I, I2, and I3 be the instantaneous values of the permanent currents at the moment of closing the circuit, t equals 0. Combined, these would give the resultant field OA. In Figure 18, the three transient currents in this moment are I degree equals I, I2, I2, I3 degree, I3, and combined these give a resultant field OB, equal and opposite to OA. In Figure 18, the permanent field rotates synchronously on the concentric circle A, the transient field OB remains constant in the direction OB. Since all three transient components of current decrease in proportion to each other, it decreases, however, with the decrease of the transient current, that is, shrinks together on the line B. The resultant or actual field thus is the combination of the permanent fields, shown as OA OA2, and the transient fields, shown as OB1, OB2, etc., and derived thereby by the parallelogram law, as shown in Figure 18, as OC1, OC2, etc. In this diagram, B1 C1, B2 C2 etc., are equal to OA1, OA2, etc., that is, to the radius of the permanent circle A. That is, while the rotating field in permanent condition is represented by the concentric circle A, the resultant field during the transient or starting period is represented by a succession of arcs of circles C, the centers of which move from B. In the moment of start, on the line B, O toward 0, and can be constructed hereby by drawing from the successive points B0, B1, B2, which correspond to successive moments of time 0, T1, T2, radii BC, B2C2, etc., under the angles, that is, in the direction corresponding to the time 0, T1, T2 etc. This is done in Figure 19, and thereby the transient of the rotating field is constructed. From this polar diagram of the rotating field, in Figure 19, values OC can now be taken, corresponding to successive moments of time, and plotted in rectangular coordinates, as done in Figure 20. As seen, the rotating field builds up from 0 at the moment of closing the circuit, and reaches the final value by a series of oscillations, that is, it first reaches beyond the permanent value, then drops below it, rises again beyond it, etc. Here we have an oscillatory transient, produced in a system with only one form of stored energy, magnetic energy, by the combination of several simple exponential transients. However, it must be considered that, while energy can be stored in one form only, as magnetic energy, it can be stored in 3 electric circuits, and a transfer of stored magnetic energy between the 3 electric circuits, and therefore a surge, thus can occur. It is interesting to note that the rotating field transient is independent of the point of the wave at which the circuit is closed. That is, while the individual transients of the 3 three-phase currents vary in shape with the point of the wave at which they start, as shown in Figure 17, their polyphase resultant always has the same oscillating approach to a uniform rotating field, of duration T equals L/R. The maximum value, which the magnetic field during the transition period can reach, is limited to less than double the final value, as is obvious from the construction of the field, Figure 19. It is evident herefrom, however, that in apparatus containing rotating fields, as induction motors, polyphase synchronous machines, etc., the resultant field may under transient conditions reach nearly double value, and if then it reaches far above magnetic saturation, excessive momentary currents may appear, similar as in starting transformers of high magnetic density. In polyphase rotary apparatus, however, these momentary starting currents usually are far more limited than in transformers, by the higher stray field, self-inductive reactance, etc., of the apparatus, resulting from the air gap in the magnetic circuit. 19. An instance of the use of the single-energy transient in engineering calculations may be considered the investigation of the momentary short-circuit phenomena of synchronous alternators. In alternators, especially high-speed high-power machines as turbo alternators, the momentary short-circuit current may be many times greater than the final or permanent short-circuit current, and this excess current usually decreases very slowly, lasting for many cycles. At the same time, a big current rush occurs in the field. This excess field current shows curious pulsations, of single and of double frequency, and in the beginning the armature currents also show asymmetrical shapes. Some oscillograms of three-phase, quarter-phase, and single-phase short circuits of turbo alternators are shown in Figures 25 to 28. By considering the transients of energy storage, these rather complex-appearing phenomena can be easily understood, and predetermined from the constants of the machine with reasonable exactness. In an alternator, the voltage under load is affected by armature reaction and armature self-induction. Under permanent condition, both usually act in the same way, reducing the voltage at non-inductive and still much more at inductive load, and increasing it at anti-inductive load, and both are usually combined in one quantity, the synchronous reactance X0. In the transients resulting from circuit changes, as short circuits, the self-inductive armature reactance and the magnetic armature reaction act vary differently. The former is instantaneous in its effect, while the latter requires time. The self-inductive armature reactance X1 consumes a voltage X1I by the magnetic flux surrounding the armature conductors, which results from the MMF of the armature current, and therefore requires a component of the magnetic field flux for its production. As the magnetic flux and the current which produces it must be simultaneous, the former being an integral part of the phenomenon of current flow, as seen in Lecture 2, it thus follows that the armature reactance appears together so also in their effect on synchronous operation, in hunting, etc. with the armature current, that is instantaneous. The armature reaction, however, is the MMF of the armature current in its reaction on the MMF of the field exciting current. That is, that part X2 equals X0, X1 of the synchronous reactance which corresponds to the armature reaction is not a true reactance at all, consumes no voltage, but represents the consumption of field ampere turns by the MMF of the armature current and the corresponding change of field flux. Since, however, the field flux represents stored magnetic energy, it cannot change instantly, and the armature reaction thus does not appear instantaneously with the armature current, but shows a transient which is determined essentially by the constants of the field circuit, that is the counterpart of the field transient of the machine. If then an alternator is short-circuited, in the first moment only the true self-inductive part 1 of the synchronous reactance exists, and the armature current thus is I1 equals E0 x1, where E0 is the induced EMF, that is, the voltage corresponding to the magnetic field excitation flux existing before the short circuit. Gradually the armature reaction lowers the field flux, in the manner as represented by the synchronous reactance XO, and the short-circuit current decreases to the value I0 equals E0 x0, the ratio of the momentary short-circuit current to the permanent short-circuit current thus is, approximately, the ratio I1 I0 equals x0 over x1, that is, synchronous reactance to self-inductive reactance, or armature reaction plus armature self-induction, to armature self-induction. In machines of relatively low self-induction and high armature reaction, the momentary short-circuit current thus may be many times the permanent short-circuit current. The field flux remaining at short circuit is that giving the voltage consumed by the armature self-induction, while the decrease of field flux between open circuit and short circuit corresponds to the armature reaction. The ratio of the open circuit field flux to the short circuit field flux thus is the ratio of armature reaction plus self-induction to the self-induction, or of the synchronous reactance to the self-inductive reactance, x0 over x1. Thus it is, momentary short circuit current over permanent short circuit current equals open circuit field flux asterisk over short circuit field flux. Armature reaction plus self-induction over self-induction equals synchronous reactance over self-inductive reactance. 20. Let equals field flux of a three-phase alternator, or, in general, polyphase alternator, at open circuit, and this alternator be short-circuited at the time t equals 0. The field flux then gradually dies down, by the dissipation of its energy in the field circuit, to the short-circuit field flux 0, as indicated by the curve in figure 2.14. If M equals ratio, armature reaction plus self-induction, over self-induction equals synchronous reactance, over self-inductive reactance it is equals M0, and the initial value of the field flux consists of the permanent part 0, and the transient part equals 1 to 0 equals M-1, 0. This is a rather slow transient, frequently of a duration of a second or more. The armature currents I1, I2, I3 are proportional to the field flux which produces them, and thus gradually decrease, from initial values, which are as many times higher than the final values as 1 is higher than 0, or m times, and are represented in Fig. 21b. The resultant MMF of the armature currents, or the armature reaction, is proportional to the currents, and thus follows the same field transient, as shown by F in Figure 21c. The field exciting current is I0 at open circuit as well as in the permanent condition of short circuit. In the permanent condition of short circuit, the field current I0 combines with the armature reaction F0, which is demagnetizing, to a resultant MMF, which produces the short circuit flux 0. During the transition period the field flux is higher than 0, and the resultant MMF must therefore be higher in the same proportion. Since it is the difference between the field current and the armature reaction F, and the latter is proportional to, the field current thus must also be asterisk if the machine were open-circuited before the short circuit, otherwise the field flux existed before the short circuit. It herefrom follows that the momentary short circuit current essentially depends on the field flux, and thereby the voltage of the machine, before the short circuit, but is practically independent of the load on the machine before the short circuit and the field excitation corresponding to this load. Proportional to thus, as it is I equals I0 at 0, during the transition period it is I equals 0 I0. Hence, the field exciting current traverses the same transient, from an initial value I0 foot to the normal value I0, as the field flux and the armature currents. Thus, at the moment of short circuit a sudden rise of field current must occur, to maintain the field flux at the initial value against the demagnetizing armature reaction. In other words, the field flux decreases at such a rate as to induce in the field circuit the EMF required to raise the field current in the proportion M, from I0 to I0 foot, and maintain it at the values corresponding to the transient I, figure 21d. As seen, the transients, I1, I2, I3, F, I are proportional to each other, and are a field transient. If the field, excited by current I0, at impressed voltage EO, were short-circuited upon itself, in the first moment the current in the field would still be IO, and therefore the voltage EO would have to be induced by the decrease of magnetic flux, and the duration of the field transient, as discussed in Lecture 3, would be to L0 over RO. The field current in figure 21d, of the alternator short-circuit transient, starts with the value I0 equals μ0, and if E0 is the EMF supplied in the field exciting circuit from a source of constant voltage supply, as the exciter, to produce the current I0, the voltage E0 equals μ0, must be acting in the field exciting circuit, that is, in addition to the constant exciter voltage EO. A voltage, M1, E0 must be induced in the field circuit by the transient of the magnetic flux. As a transient of duration L0 R0, induces the voltage E0, to induce the voltage, M-1, E0 the duration of the transient must be to equals L0, M1, R0, where low equals inductance, RO total resistance of field exciting circuit, inclusive of external resistance. The short-circuit transient of an alternator thus usually is of shorter duration than the short-circuit transient of its field, the more so, the greater M, that is, the larger the ratio of momentary to permanent short-circuit current. In Fig. 21 the decrease of the transient is shown greatly exaggerated compared with the frequency of the armature currents, and Figure 22 shows the curves more nearly in their actual proportions. The preceding would represent the short-circuit phenomena, if there were no armature transient. However, the armature circuit contains inductance also, that is, stores magnetic energy, and thereby gives rise to a transient, of duration T equals Lr, where L equals inductance, R equals resistance of the armature circuit. The armature transient usually is very much shorter in duration than the field transient. The armature currents thus do not instantly assume their symmetrical alternating values, but if in figure 21b, I, are the instantaneous values of the armature currents in the moment of start, T equals 0, three transients are superposed upon these, and start with the values I1, I2, I3. The resultant armature currents are derived by the addition of these armature transients upon the permanent armature currents, in the manner as discussed in paragraph 18, except that in the present case even the permanent armature currents I1, I2, I3 are slow transients. In Fig. 22b are shown the three armature short-circuit currents, in their actual shape as resultant from the armature transient and the field transient. The field transient, or rather its beginning, is shown as Figure 22a. Figure 22b gives the three armature currents for the case where the circuit is closed at the moment when I should be maximum. I then shows the maximum transient, and I2 and is transients in opposite direction, of half amplitude. These armature transients rapidly disappear, and the three currents become symmetrical, and gradually decrease with the field transient to the final value indicated in the figure. The resultant MMF of three three-phase currents, or the armature reaction, is constant if the currents are constant, and as the currents decrease with the field transient, the resultant armature reaction decreases in the same proportion as the field, as is shown in Figure 21c by F. During the initial part of the short circuit, however, while the armature transient is appreciable and the armature currents thus unsymmetrical, as seen in Figure 22b, their resultant polyphase MMF also shows a transient, the transient of the rotating magnetic field discussed in paragraph 18. That is, it approaches the curve F of Figure 21c by a series of oscillations, as indicated in Figure 21e. Since the resultant MMF of the machine, which produces the flux, is the difference of the field excitation, Figure 21d, and the armature reaction, then if the armature reaction shows an initial oscillation, in Figure 21e, the field exciting current must give the same oscillation, since its MMF minus the armature reaction gives the resultant field excitation corresponding to flux. The starting transient of the polyphase armature reaction thus appears in the field current, as shown in Figure 22c, as an oscillation of full machine frequency. As the mutual induction between armature and field circuit is not perfect, the transient pulsation of armature reaction appears with reduced amplitude in the field current, and this reduction is the greater, the poorer the mutual inductance, that is, the more distant the field winding is from the armature wind-ing. In Fig. 22c a damping of 20% is assumed, which corresponds to fairly good mutual inductance between field and armature, as met in turbo alternators. If the field exciting circuit contains inductance outside of the alternator field, as is always the case to a slight extent, the pulsations of the field current, Figure 22c, are slightly reduced and delayed in phase, and with considerable inductance intentionally inserted into the field circuit. The effect of this inductance would require consideration. From the constants of the alternator, the momentary short circuit characteristics can now be constructed. Assuming that the duration of the field transient is equals L0, M1, R0, equals 1 second, the duration of armature transient is T equals LR equals 1 second. And assuming that the armature reaction is 5 times the armature self-induction, that is, the synchronous reactance is 6 times the self-inductive reactance, X0 X1 equals M equals 6. The frequency is 25 cycles. If is the initial or open circuit flux of the machine, the short circuit flux is 0 equals 1 M equals 16, and the field transient is a transient of duration 1 second, connecting in 0. Figure 22a, represented by the expression equals 0 plus 0, epsilon, T2. The permanent armature currents I1, I2, I3 then are currents starting with the values ME0 X0 and decreasing to the final short circuit current E0 X0 on the field transient of duration T0. To these currents are added the armature transients, of duration T, which start with initial values equal but opposite in sign to the initial values of the permanent, or rather slowly transient, armature currents, as discussed in paragraph 18, and thereby give the asymmetrical resultant currents. Figure 22b. The field current I gives the same slow transient as the flux, starting with I0 equals μ0, and tapering to the final value I0. Upon this is superimposed the initial full-frequency pulsation of the armature reaction. The transient of the rotating field, of duration t equals 0.1 second, is constructed as in paragraph 18, and for its instantaneous values the percentage deviation of the resultant field from its permanent value is calculated. Assuming 20% damping in the reaction on the field excitation, the instantaneous values of the slow field transient, that is, of the current, I0, since I0 is the permanent component, then are increased or decreased by 80% of the percentage variation of the transient field of armature reaction from uniformity, and thereby the field curve, Figure 22c, is derived. Here the correction for the external field inductance is to be applied, if considerable. Since the transient of the armature reaction does not depend on the point of the wave where the short circuit occurs, it follows that the phenomena at the short circuit of a polyphase alternator are always the same, that is, independent of the point of the wave at which the short circuit occurs, with the exception of the initial wave shape of the armature currents, which individually depend on the point of the wave at which the phenomenon begins, but not so in their resultant effect. 21. The conditions with a single-phase short circuit are different, since the single-phase armature reaction is pulsating, varying between 0 and double its average value, with double the machine frequency. The slow field transient and its effects are the same as shown in Figure 21, A to D. However, the pulsating armature reaction produces a corresponding pulsation in the field circuit. This pulsation is of double frequency, and is not transient, but equally exists in the final short circuit current. Furthermore, the armature transient is not constant in its reaction on the field, but varies with the point of the wave at which the short circuit starts. Assume that the short circuit starts at that point of the wave where the permanent, or rather slowly transient, armature current should be 0, then no armature transient exists, and the armature current is symmetrical from the beginning, and shows the slow transient of the field, as shown in Figure 23, where A is the field transient, the same as in Figure 22a, and B the armature current, decreasing from an initial value, which is m times the final value, on the field transient. Assume then that the mutual induction between field and armature is such that 60% of the pulsation of armature reaction appears in the field current. 40% damping for the double frequency reaction would about correspond to the 20% damping assumed for the transient full frequency pulsation of the polyphase machine. The transient field current thus pulsates by 60% around the slow field transient, as shown by Figure 23c, passing a maximum for every maximum of armature current, and thus maximum of armature reaction, and a minimum for every zero value of armature current, and thus armature reaction. Such single-phase short-circuit transients have occasionally been recorded by the oscillograph, as shown in Figure 27. Usually, however, the circuit is closed at a point of the wave where the permanent armature current would not be zero, and an armature transient appears, with an initial value equal, but opposite to, the initial value of the permanent armature current. This is shown in Figure 24 for the case of closing the circuit at the moment ere the armature current should be a maximum, and its transient thus a maximum. The field transient is the same as before. The armature current shows the initial asymmetry resulting from the armature transient, and superimposed on the slow field transient. On the field current, which, due to the single-phase armature reaction, shows a permanent double-frequency pulsation, is now superimposed the transient full-frequency pulsation resultant from the transient armature reaction, as discussed in paragraph 20. Every second peak of the permanent double-frequency pulsation then coincides with a peak of the transient full-frequency pulsation, and is thereby increased, while the intermediate peak of the double-frequency pulsation coincides with a minimum of the full-frequency pulsation, and is thereby reduced. The result is that successive waves of the double-frequency pulsation of the field current are unequal in amplitude, and high and low peaks alternate. The difference between successive double-frequency waves is a maximum in the beginning, and gradually decreases, due to the decrease of the transient full-frequency pulsation, and finally the double-frequency pulsation becomes symmetrical, as shown in Figure 24c. In the particular instance of Figure 24, the double frequency and the full frequency peaks coincide, and the minima of the field current curve thus are symmetrical. If the circuit were closed at another point of the wave, the double frequency minima would become unequal, and the maxima more nearly equal, as is easily seen. While the field exciting current is pulsating in a manner determined by the full-frequency transient and double-frequency permanent armature reaction, the potential difference across the field winding may pulsate less, if little or no external resistance or inductance is present, or may pulsate so as to be nearly alternating and many times higher than the exciter voltage, if considerable external resistance or inductance is present, and therefore it is not characteristic of the phenomenon, but may become important by its disruptive effects, if reaching very high values of voltage. With a single-phase short circuit on a polyphase machine, the double-frequency pulsation of the field resulting from the single-phase armature reaction induces in the machine phase, which is in quadrature to the short-circuited phase, an EMF which contains the frequencies f, 2 plus or minus 1, that is, full frequency and triple frequency. And as the result an increase of voltage and a distortion of the quadrature phase occurs, as shown in the oscillogram. Figure 25. Various momentary short-circuit phenomena are illustrated by the oscillograms Figures 26 to 28. Figs. 264 and 26b show the momentary three-phase short circuit of a four-polar 25-cycle 1500 kW steam turbine alternator. The lower curve gives the transient of the field, exciting current, the upper curve that of one of the armature currents, in Figure 26a that current which should be near zero, in Figure 26b that should be near its maximum value at the moment where the short circuit starts. Figure 27 shows the single-phase short circuit of a pair of machines in which the short circuit occurred at the moment in which the armature short circuit current should be zero. The armature current wave, therefore, is symmetrical, and the field current shows only the double-frequency pulsation. Only a few half-waves were recorded before the circuit breaker opened the short circuit. Figure 28 shows the single-phase short circuit of a 6-polar 5000 kW 11,000-volt steam turbine alternator, which occurred at a point of the wave where the armature current should be not far from its maximum. The transient armature current, therefore, starts unsymmetrical, and the double-frequency pulsation of the field current shows during the first few cycles the alternate high and low peaks resulting from the superposition of the full-frequency transient pulsation of the rotating magnetic field of armature reaction. Interesting in this oscillogram is the irregular initial decrease of the armature current and the sudden change of its wave shape, which is the result of the transient of the current transformer, through which the armature current was recorded. On the true armature current transient superposes the starting transient of the current transformer. Figure 25 shows a single-phase short circuit of a quarter-phase alternator. The upper wave is the voltage of the phase which is not short-circuited, and shows the increase and distortion resulting from the double-frequency pulsation of the armature reaction. Lecture V. Single-energy transient of ironclad. Circuit 22. Usually in electric circuits, current, voltage, the magnetic field and the dielectric field are proportional to each other, and the transient thus is a simple exponential, if resulting from one form of stored energy, as discussed in the preceding lectures. This, however, is no longer the case if the magnetic field contains iron or other magnetic materials, or if the dielectric field reaches densities beyond the dielectric strength of the carrier of the field, etc., and the proportionality between current or voltage and their respective fields, the magnetic and the dielectric, thus ceases, or, as it may be expressed, the inductance L is not constant, but varies with the current, or the capacity is not constant, but varies with the voltage. The most important case is that of the ironclad magnetic circuit, as it exists in one of the most important electrical apparatus, the alternating current transformer. If the iron magnetic circuit contains an air gap of sufficient length, the magnetizing force consumed in the iron, below magnetic saturation, is small compared with that consumed in the air gap, and the magnetic flux, therefore, is proportional to the current up to the values where magnetic saturation begins. Below saturation values of current, the transient thus is the simple exponential discussed before. If the magnetic circuit is closed entirely by iron, the magnetic flux is not proportional to the current, and the inductance thus not constant, but varies over the entire range of currents, following the permeability curve of the iron. Furthermore, the transient due to a decrease of the stored magnetic energy differs in shape and in value from that due to an increase of magnetic energy, since the rising and decreasing magnetization curves differ, as shown by the hysteresis cycle. Since no satisfactory mathematical expression has yet been found for the cyclic curve of hysteresis, a mathematical calculation is not feasible, but the transient has to be calculated by an approximate step-by-step method, as illustrated for the starting transient of an alternating current transformer in Transient Electric Phenomena and Oscillations, Section 1, Chapter 12. Such methods are very cumbersome and applicable only to numerical instances. An approximate calculation, giving an idea of the shape of the transient of the ironclad magnetic circuit, can be made by neglecting the difference between the rising and decreasing magnetic characteristic, and using the approximation of the magnetic characteristic given by Froelic's formula. Plus, which is usually represented in the form given by Kennelly. Plus. That is, the reluctivity is a linear function of the field intensity. It gives a fair approximation for higher magnetic densities. This formula is based on the fairly rational assumption that the permeability of the iron is proportional to its remaining magnetizability. That is, the magnetic flux density consists of a component, the field intensity, which is the flux density in space, and a component equals, which is the additional flux density carried by the iron. Is frequently called the metallic flux density. With increasing, reaches a finite limiting value, which in iron is about infinity equals 20,000 lines per cm2. At any density, the remaining magnetizability then is infinity, and, assuming the metallic permeability as proportional. Here too, gives mu equals C, infinity, and, substituting mu equals, gives C infinity 1 plus C. As seen, in the ironclad transient the current curve is very much steeper in the range of high currents, where magnetic saturation is reached, but the current is slower in the range of medium magnetic densities. Thus, in ironclad transients very high current values of short duration may occur, and such transients, as those of the starting current of alternating current transformers, may therefore be of serious importance by their excessive current values. An oscillogram of the voltage and current waves in an 11,000 kilowatts high voltage 60-cycle 3-phase transformer, when switching onto the generating station near the most unfavorable point of the wave, is reproduced in Figure 30. As seen, an excessive current rush persists for a number of cycles, causing a distortion of the voltage wave, and the current waves remain unsymmetrical for many cycles. Lecture 6. Double energy transients. In a circuit in which energy can be stored in one form only, the change in the stored energy which can take place as the result of a change of the circuit conditions is an increase or decrease. The transient can be separated from the permanent condition, and then always is the representation of a gradual decrease of energy. Even if the stored energy after the change of circuit conditions is greater than before, and during the transition period an increase of energy occurs, the representation still is by a decrease of the transient. This transient then is the difference between the energy storage in the permanent condition and the energy storage during the transition period. If the law of proportionality between current, voltage, magnetic flux, etc. applies, the single energy transient is a simple exponential function, equals 0, tt0 where 0 equals initial value of the transient, and t0 equals duration of the transient, that is, the time which the transient voltage, current, etc. would last if maintained at its initial value. The duration T0 is the ratio of the energy storage coefficient to the power dissipation coefficient. Thus, if energy is stored by the current I, as magnetic field, T0 equals Lr, where L equals inductance coefficient of energy storage by the current, R equals resistance equals coefficient of power dissipation by the current. If the energy is stored by the voltage E, as dielectric field, the duration of the transient would be T0 foot equals Cg, where C equals capacity equals coefficient of energy storage by the voltage, in the dielectric field, and G equals conductance coefficient of power consumption by the voltage, as leakage conductance by the voltage, corona, dielectric hysteresis, etc. Thus the transient of the spontaneous discharge of a condenser would be represented by E equals E0 epsilon GCT. Similar single-energy transients may occur in other systems. For instance, the transient by which a water jet approaches constant velocity when falling under gravitation through a resisting medium would have the duration T equals V0g, where V0 equals limiting velocity, g equals acceleration of gravity, and would be given by V equals V0, 1 epsilon, tt. In a system in which energy can be stored in two different forms, as for instance as magnetic and as dielectric energy in a circuit containing inductance and capacity, in addition to the gradual decrease of stored energy similar to that represented by the single energy transient, a transfer of energy can occur between its two different forms. Thus, if equals transient current, E equals I transient voltage, that is, the difference between the respective currents and voltages existing in the circuit as result of the previous circuit condition, and the values which should exist as result of the change of circuit conditions, then the total stored energy is W equals Li22 plus Su22 equals Wm plus Wd. While the total energy W decreases by dissipation, Wm may be converted into Wd, or inversely. Such an energy transfer may be periodic, that is, magnetic energy may change to dielectric and then back again, or unidirectional, that is, magnetic energy may change to dielectric, or inversely, dielectric to magnetic, but never change back again, but the energy is dissipated before this. This latter case occurs when the dissipation of energy is very rapid, the resistance, or conductance, high, and therefore gives transients, which rarely are of industrial importance, as they are of short duration and of low power. It therefore is sufficient to consider the oscillating double-energy transient, that is, the case in which the energy changes periodically between its two forms, during its gradual dissipation. This may be done by considering separately the periodic transfer, or pulsation of the energy between its two forms, and the gradual dissipation of energy. Pulsation of energy. The magnetic energy is a maximum at the moment when the dielectric energy is zero, and when all the energy, therefore, is magnetic, and the magnetic energy is then Li022, where I0 equals maximum transient current. The dielectric energy is a maximum at the moment when the magnetic energy is zero, and all the energy therefore dielectric and is then So022 where E0 equals maximum transient voltage. As it is the same stored energy which alternately appears as magnetic and as dielectric energy, it obviously is Li022 equals So022. This gives a relation between the maximum transient current and the maximum transient voltage. E0I0 equals LC. Elk therefore is of the nature of an impedance ZO, and is called the natural impedance, or the surge impedance, of the circuit, and its reciprocal, LC equals 0, is the natural admittance, or the surge admittance, of the circuit. The maximum transient voltage can thus be calculated from the maximum transient current, E0 equals I0 LC equals I0 Z0 and inversely, I0 equals E0 CL equals E0 Y0. This relation is very important, as frequently in double energy transients one of the quantities E0 or I0 is given, and it is important to determine the other. For instance, if a line is short-circuited, and the short-circuit current I0 suddenly broken, the maximum voltage which can be induced by the dissipation of the stored magnetic energy of the short-circuit current is E0 equals I0 Z0. If one conductor of an ungrounded cable system is grounded, the maximum momentary current which may flow to ground is I0 equals E0 Y0, where E0 equals voltage between cable conductor and ground. If lightning strikes a line, and the maximum voltage which it may produce on the line, as limited by the disruptive strength of the line insulation against momentary voltages, is E0, the maximum discharge current in the line is limited to I0 equals E0 Y0. If L is high but C low, as in the hypotential winding of a high-voltage transformer, which winding can be considered as a circuit of distributed capacity, inductance, and resistance, ZO is high and YO low. That is, a high transient voltage can produce only moderate transient currents, but even a small transient current produces high voltages. Thus reactances, and other reactive apparatus, as transformers, stop the passage of large oscillating currents, but do so by the production of high oscillating voltages. Inversely, if L is low and C high, as in an underground cable, ZO is low but YO high, and even moderate oscillating voltages produce large oscillating currents, but even large oscillating currents produce only moderate voltages. Thus underground cables are little liable to the production of high oscillating voltages. This is fortunate, as the dielectric strength of a cable is necessarily relatively much lower than that of a transmission line, due to the close proximity of the conductors in the former. A cable, therefore, when receiving the moderate or small oscillating currents which may originate in a transformer, gives only very low oscillating voltages, that is, acts as a short circuit for the transformer oscillation, and therefore protects the latter. Inversely, if the large oscillating current of a cable enters a reactive device, as a current transformer, it produces enormous voltages therein. Thus, cable oscillations are more liable to be destructive to the reactive apparatus, transformers, etc. connected with the cable, than to the cable itself. A transmission line is intermediate in the values of Z0 and Y0 between the cable and the reactive apparatus, thus acting like a reactive apparatus to the former, like a cable toward the latter. Thus, The transformer is protected by the transmission line in oscillations originating in the transformer, but endangered by the transmission line in oscillations originating in the transmission line. The simple consideration of the relative values of Z0 equals LC in the different parts of an electric system thus gives considerable information on the relative danger and protective action of the parts on each other, and shows the reason why some elements, as current transformers, are far more liable to destruction than others, but also shows that disruptive effects of transient voltages, observed in one apparatus, may not and very frequently do not originate in the damaged apparatus, but originate in another part of the system, in which they were relatively harmless, and become dangerous only when entering the former apparatus. 26. If there is a periodic transfer between magnetic and dielectric energy, the transient current I and the transient voltage, E, successively increase, decrease, and become zero. The current thus may be represented by I equals I0 cos, where I0 is the maximum value of current, discussed above, and equals 2 pi ft, where f equals the frequency of this transfer, which is still undetermined, and the phase angle at the starting moment of the transient, that is, I equals I0 cos equals initial transient current. As the current I is a maximum at the moment when the magnetic energy is a maximum and the dielectric energy zero, the voltage, E, must be zero when the current is a maximum, and inversely, and if the current is represented by the cosine function, the voltage thus is represented by the sine function, that is, E0 equals sin